Okay, thank you, Soterius, and thank you, everyone. It's a real pleasure for me to be here today. So I'm going to be telling you about some recent results in quantum sensors for fundamental physics experiments. And it's going to be a little bit more specialized than what people normally talk about when they say quantum sensors. It's going to be very specifically on the technologies that the quantum computing community has been developing and deploying those very, very sensitive technologies which manipulate information at the single quantum level, and using those to try to further our goals in high energy physics, particle physics, and cosmology. And so in particular, I'm going to be focusing today on investigations of experiments searching for cold dark matter using things like superconducting qubits. So here's an actual image of three superconducting qubits, which are each based on Josephson junctions. So this is of a style very similar to that used by Google or by IBM, a typical transmon style superconducting qubit. I'm going to try to get through three separate topics, and we'll see how far we get. And since these are three separate topics, if people have questions, please just go ahead and interrupt me and ask, and don't wait until the end because I'm going to be jumping ahead. So the first topic is reconstructing events in quantum sensor arrays made of qubits like this, using the technology of the modern quantum error correcting codes. Second topic is the information that's stored in these qubits often gets put into quantum random access memory microwave cavities. And I'll show you how forces from dark matter can induce errors in this quantum RAM that we can probe using these kinds of qubits to do photon counting or counting of individual excitations. Individual single photon signals. And then finally, if I have time, I'm going to try to speed up time using non-Gaussian probe states of the kind that's used in continuous variable quantum computing or bosonic quantum computing, as it's often called. Okay, so I'll just jump right into it. So this all started, I would say, maybe about 10 years ago, when a group of us, including myself, working in the dark matter community, noticed that the experimental platforms that people use for quantum computing look exactly like our dark matter searches, in which we have some very, very sensitive device, whether it's a detector that was optimized for dark matter, or whether it's a chip with a bunch of qubits on it used for quantum computations. And it would be placed at the 10 millikelvin stage of a dilution refrigerator inside a vacuum chamber and a cryostat with many, many layers of radiation shields. And the purpose of these many, many layers is to block sound and heat and light from the room from entering and scrambling the quantum information or creating backgrounds for your dark matter searches. So of course, the dark matter cannot be blocked by all this metal because it's not electrically charged, or at least it's got tiny electric charge at most. So the dark matter will fly right through all of this shielding. And if it occasionally scatters on your device, it can create an error in the qubit itself, or it can create an error in this quantum memory. And either way, it'll scramble the information in the quantum computation, and the signal is that your quantum computer crashes. Okay, so these kinds of qubits have a typical excitation energy of 10 to the minus 4 electron volts, which can be compared to the 1 electron volt excitation energy of a silicon-based quantum computer. So in principle, devices based on quantum computers can have much lower energy thresholds when you're trying to detect very small energy deposits from these very, very weakly interacting particles. Okay, and so conversely, I already said that the quantum computers look like our dark matter experiments. So similarly, they're going to face the same backgrounds as our dark matter experiments. So photon leakage through the cracks of the devices, depositing energy in the detectors, ionizing radiation. So muons will fly right through, probably neutrons will fly right through if there's not a lot of hydrogen in the way, and alphas might fly right through as well. Ionizing radiation typically deposits a capital MeV, 10 to the 6 electron volts per centimeter, which is huge compared to the energy scale of these devices. And as the energy scale of these devices is so low that we even have to worry about mechanical stress release. Okay, so if we mount the chips in here in a way that creates a lot of tension, eventually that tension will be released, and we'll see electron volt backgrounds that will also create detectable energy deposits. Okay, so just moving on, specifically when we talk about the qubits of quantum computing, I'm going to draw the analogy to real atoms. So we use Josephson junction LC oscillators for our superconducting qubits, but they look different from real atoms, but they have the same useful properties in that these are very nonlinear potentials and create anharmonic oscillators. Okay, so the -1 over R Coulomb potential that binds an electron to a nucleus is about as far from a harmonic quadratic potential as you can imagine. And because the restoring force depends on the distance of the orbit, we see that this phenomena that the energy levels have splittings that are not the same as each other. It's not a harmonic potential. These splittings are not non-degenerate. So you can pick any two of these levels and form a two-level system and define your qubit based on those two transitions between those two energy levels. For a Josephson junction, which you can think of as two strips of superconductor that are separated by a narrow insulating layer, and these are very tiny, this is like a couple hundred nanometer scale. What happens is you have a Cooper pair fluid that lives in one superconductor and a Cooper pair fluid that lives in the other superconductor. And because there's two distinct fluids, they can have two different phases. And so as the phase changes, the Josephson equations tell us that this Cooper pair fluid will induce a tunneling current that sloshes or oscillates between the two pieces of superconductor. And this tunneling current has a very nonlinear inductance, and that creates kind of a potential energy function that looks like a cosine function. Near the bottom of the cosine function, it kind of looks like a harmonic potential, but it becomes very, very clear as you reach the top that the energy levels spacings are very different. Okay, so again, we can pick two of these levels and use these as a two-level system to do our quantum computations. More generally, the nonlinearity of these potentials becomes a resource for creating exotic quantum states, as I hopefully will show later. Okay. So there was a lot of press about this, about catastrophic events due to ionizing radiation in these superconducting qubits. So I think way back in 2001, Google first reported that their Sycamore chip observed catastrophic error bursts when a cosmic ray or some natural radiation passes through the substrate of their quantum computing chip. And again, I told you this like a millimeter thick substrate. So as the cosmic ray flies through, it perhaps releases 100 keV, kilo electron volts of energy in electron hole pairs, which then recombine and release their energy as heat, as phonons. Okay, so there's 100 keV of energy in phonons being released. The phonons bounce around inside the silicon substrate until they reach the superconducting layer. They enter the superconductor and they scatter on the Cooper pairs to break the Cooper pairs into charged quasiparticles. As I mentioned, the energy barrier, the binding energy of the Cooper pairs in the superconductor is about 10 to the -4 electron volts. Okay, so going through the numbers again, 100 kilo electron volts, that's 10 to the 5 electron volts of energy. It only takes 10 to the -4 electron volts to break each pair. So we're talking about 10 to the 9 broken pairs. And so what Google observed was that every single qubit on their chip was simultaneously wiped out by this energy deposit. And the mechanism by which the information is lost is here's where the Josephson junction is, the two pieces of superconductor. And the qubit oscillator is, again, the sloshing of the Cooper pair fluid back and forth across this gap. Okay, so if one of these charged particles comes through, and then there's this charged Cooper pair oscillator sloshing back and forth, then this kind of becomes like a kid on a swing and a soccer ball, and the kid can accidentally hit the soccer ball and kick the soccer ball, transferring its kinetic energy to the quasi-particle. And in that process, if there was originally one quantum of oscillation in that qubit, it will de-excite to 0 quantum excitation, and that quantum information stored in this qubit has been wiped out. Okay. More recently, with the Willow chip, just in December of last year, Google used gap engineering. They engineered a potential energy barrier so that the quasi-particles could not enter this junction, and therefore they would not be impacted by the oscillatory motion of the Cooper pair fluid. And so that greatly decreased their error rate so that they could only see the highest energy events where the quasi-particles were energetic enough to jump over the potential barrier and then get kicked by the qubit oscillator. So they reduced, by doing this potential energy gap engineering, they were able to reduce their event rate from a 1 per minute catastrophic event to 1 per hour event rate of events that kind of look like this. So this is an array of 29 qubits. And here they can, what's plotted in a color scale is the probability at any time of detecting an error in that qubit in which the information has been wiped out. And so now they can localize the position of the cosmic ray hit. And more importantly, because they were able to suppress this tunneling and its energy extraction in most of the qubits, then in lower energy regions away from the point of impact, those qubits were not affected. And so they were able to infer using their quantum error correction codes, because all the qubits here were fine and the qubits here were fine, but the qubits in the middle were not okay. They were able to error correct by taking the data over here and copying it back over here. Okay, that's not exactly how it's done, but roughly that's how it's done. So they were able to not only reconstruct the morphology of all 6 of their events that they took over a 6-hour run period, but they were also able to successfully recover the data that was wiped out, that was locally wiped out. Okay, so then there have been more recent proposals to use these kinds of error correcting codes to actually reconstruct particle trajectories. So imagine if you made a quantum sensor array out of these qubits, then when you define what are called logical qubits based on strings of physical qubits, so these are 2 logical qubits, where the information, the 0 or 1, is kind of stored collectively across many of the physical qubits. Okay, and then that kind of protects you against individual qubit errors that are shown in red. So here there's 7 qubits, and if 6 of them kind of say the same thing, and 1 of them says something different, then because you stored the information in a way that's dispersed across all 7 qubits, you can infer that this one was incorrect and fix it. Okay, here's an example where you have 2 of these logical qubits, and a cosmic ray flies through and hits all 7 of these. And again, here it's one that wasn't working. So the present day qubits don't work that well. So it's not uncommon to find one that's not working. But now you find 6 in a row that all got hit. So then you can tell that the cosmic ray came from this direction and it came along this trajectory and not this trajectory. And so this is all very familiar from doing particle reconstruction in our particle physics tracking detectors. But it turns out the quantum computing people are doing exactly the same thing, and they're just using a different language, and they're calling them logical qubits. So again, physical qubit error can be identified as noise because it's not correlated, and logical qubit error is an actual track going through this quantum sensor array. Another nice thing about this is you do not have to predefine the logical qubits before you take the data. You can take the data beforehand and set all qubits equal to 0, and then you look for ones that spontaneously appear, or alternatively you set them all to 1s and you look for them to decay to 0. And you can define your logical qubits after the fact. So for example, if you have a detector that's kind of tracking the sun, you're only looking for events that come from the direction of the sun or from some other astrophysical source, and you have a collection of qubits. You can define these logical qubits to point in different directions during your data analysis. You don't have to do it beforehand. So that's another way of nicely implementing kind of directional detection of events of dark matter, of exotic particles from astrophysical sources. Yes, please.
The way you presented, basically bits and not just qubits. Is there a difference between the 2 type of error you can have? Like, is there only the information is only on amplitude of the bit flip, or is there something in phase also?
It could be both, and I think you're absolutely right. I'm trying to make the connection for what we would do normally in kind of classical analysis of tracks. I'm trying to make the point that when you do the actual quantum error correction, which is a little bit more complicated, there's a direct mapping to what we're already doing in classical computations. And if you like, later on, I can talk a little bit more about how the quantum error correction actually happens, because it turns out that because the qubit is stored in quantum information here, either in the X or the sigma X or the sigma Z basis, you cannot actually measure each individual qubit without destroying the information, because sigma X does not commute with sigma Z. So you cannot measure Z without scrambling X. And the Z information is the amplitude information. The X information is the phase information. And so there's more complicated ways that you may know of doing the checking for errors. So basically, you check for pairs of qubits. You can ask the question: is the state of this qubit the same as the state of this qubit, or is it different? Okay, without asking exactly what is the state of each individual qubit. So you have to check them pairwise, or you check them 4 at a time. And so you check whether they're all the same or if they are not the same. And those are the kinds of questions that you're allowed to ask. But in the end, regardless of how it's actually done, how the checking of what's called the stabilizers of the qubit is actually done, the principles of how we would detect tracks and reconstructive event morphologies ends up the same as what we would normally think of. Okay, so then I just want to quickly advertise that we do, at Fermilab, we do have this new facility, which is a 10 millikelvin dilution refrigerator that's located 100 meters underground in one of the neutrino beamlines. And so here's the clean room in the tunnel, and then the dilution refrigerator inside. And so this is part of our quantum science center that we have at Fermilab. And it's the first underground dedicated facility in the US, at least, to be operating qubits deep underground to protect them from cosmic rays and things like that. I believe there's also a similar facility in Gran Sasso. Okay. So now I'll move on to the... Yes,
is there quantum activity in Gran Sasso? It is only for dark matter search.
I believe it's
computing, some quantum computing.
I actually don't know. I believe it's a test stand for the core neutrinos double beta decay. Yeah.
For search.
Yeah. But they do operate qubits down there. Just I think parasitically. Yes.
What qubits they operate?
I believe they operate also superconducting qubits based on granular aluminum.
Okay.
Yeah, and then they measure. They try to see if they can protect the qubits from the cosmic rays. And I only mention it because it's a little bit closer. If people here want to work on that, it's a little bit closer to go to Gran Sasso. Okay. So I'm going to move on to the second part of the talk, which is going to be a little bit longer, which is dark matter overwriting data stored in your quantum random access memory. Okay, so do you folks know about the QCD axion dark matter?
Not everybody.
Not everybody. So maybe I'll give a quick introduction. I'm never sure whether to do this because it takes a little bit of time. So there's the QCD axion, which is motivated by the strong CP charge parity violation problem, which can be stated as why is the neutron electric dipole moment observed to be too small, so small and so vanishingly small. So the first experiments were done by Norman Ramsey way back in the 1950s. With neutron interferometry experiments, in which the reasoning was that if you have a neutron whose size is its Compton wavelength, about 10 to the minus 15 meters, and it's charge neutral, do we really know whether the neutron is composite or not, made out of charged components? We do know now that it's made up of quarks, so up and down quarks that are charged. He didn't know back then, but it was a perfectly valid hypothesis. And with this hypothesis, if you assume the charges inside this bag are approximately 1 electron charge, and you know the size, then you can kind of make a guess as to what the electric dipole moment of this object ought to be. And so they guessed about 10 to the minus 16 e centimeters. And in the very first experiment, they observed closer to 10 to the minus 18. Okay, so that was very puzzling. And then over the next 70 years, the experiments have been more and more precise by like almost 10 orders of magnitude until we're down at kind of 10 to the minus 10 of what the naive prediction would be for the charge asymmetry inside a neutron. So this is very, very puzzling because there's nothing in the theory of the strong force, quantum thermodynamics, that tells you that the charge distribution inside a neutron has to be symmetric. Okay, so if it were completely symmetric, there'd be no charge separation between positive and negative charges. But there's nothing in the theory that tells you that the ground state wave function of the neutron has to be like that. And so this is one of the longest standing problems in fundamental physics. Okay, all right, so let's see, let's go on. So this kind of charge asymmetry ends up being parameterized by a CP violating angle theta. Okay, and theta naively in quantum chromodynamics should be of order 1, because if it wasn't, you would ask why is it so much smaller than 1? And instead it's been observed to be of order 10 to the minus 10 or smaller. Okay, so then there's a theory to produce this by creating, so this is the potential energy function of some new complex scalar field, because we know scalar fields like the Higgs, and we know them from superconductivity and stuff. So there's the theorists that made a model in which there's some phase transition at some very, very high energy scale in the early universe, greater than when the temperature was greater than 10 to the 9 GeV. Okay, so you get the phase transition, and then you have kind of a Higgs degree of freedom that goes radially. But in addition, there's a Goldstone boson that goes azimuthally around the well of this wine bottle potential. That's this Goldstone boson, if you study particle physics, in the case of a broken gauge theory, gets absorbed as the longitudinal component of massive gauge bosons. Okay, the gauge bosons then have 3 degrees of freedom, 3 polarizations. But if this was a global symmetry that was broken, then there's no gauge bosons around, and this massless Goldstone boson becomes its own independent degree of freedom. Okay, pseudoscalar field. And then the second ingredient here was they took this azimuthal degree of freedom that I call arg-A here, and they coupled it to the gluon condensate that would emerge during the QCD phase transition when the quarks and gluons condense into protons, neutrons, and pions. Okay, so it turns out that the CP violating angle also couples in exactly the same way. And so you have this phase plus any pre-existing CP violating angles that might come from the QCD sector, it might come from the electroweak sector, okay, it might come from new physics, but it was all pre-existing. And then if you look at this total thing, the combination of 3 different angles that's multiplying this gluon field, if this gluon field takes non-zero expectation value, then to minimize the potential energy, this phase angle will have a potential associated with it, and it will roll down that potential until it zeroes out any pre-existing CP violating angles. Okay, and that's can be modeled in this diagram as this wine bottle potential becoming tilted, so that if you started at some value in which the total argument were non-zero, then this dynamical field would automatically roll down to its minimum and zero out all of the CP violation, and that would explain why the neutron has no electric dipole moment. Okay. So this was called the Peccei-Quinn model, but from Roberto Peccei and Helen Quinn in the 1970s. And it was almost immediately pointed out that anytime you have a quadratic minimum of a potential, you can have quantum excitations of it. So you have a new particle, which is the individual quantum excitations about this minimum. And then it was pointed out that this kind of particle, if it were very, very low in mass, its lifetime might be larger than the age of the universe. And so immediately you had a dark matter candidate. Okay, so this was called the axion. And it also provides okay, so there's two facts about it. One is there's a natural scale for the initial potential energy. That's the energy source that creates the dark matter. So it's where this field initially starts, but typical value would be the energy density of the quark gluon plasma, lambda QCD to the 4th power. And that would be the energy source that produces the dark matter. And then the second prediction then is that at this quadratic minimum, just like any harmonic oscillator potential, the shape of this parabola at this minimum would determine the frequency of these oscillations, and that corresponds to the mass of the dark matter. And so you can easily pick out that the mass of the dark matter would be this lambda QCD scale squared divided by the original temperature scale. Okay, so this parameter, this model, it tends to be very predictive, and people have been chasing for the QCD axion dark matter, I think, since the 1980s. It's very, very difficult to detect. Okay, so just to go into a little bit more detail, this axion dark matter is waves of this oscillating CP violating angle. So we know the average value of it ought to be 0 because the neutron electric dipole moment is 0. But specifically, we see that around the minimum of the potential, there will be oscillations of this CP violating angle sloshing back and forth. So there's a prediction that the neutron ought to have an AC CP violating angle, which people are now searching for. And the other prediction is that all this axion dark matter is sloshing back and forth, looks like dark matter, and so it feels gravity, and so it gets concentrated in gravitational potential wells as there's instability towards gravitational collapse. And so you end up in galaxies, you have bosonic waves with very, very large occupation number, classical occupation numbers. This dark matter comes to us in this form, not as individual particles, but as waves with like 10 to the 20 quanta per mode. Okay, sloshing back and forth. And the other prediction you can make is what is the amplitude of these waves? And so what you do is you compare the local dark matter density, so at a GeV per cubic centimeter, to the nuclear matter density, quark gluon plasma density of lambda QCD to the fourth. And the local density tells you how far this coherent bosonic wave can climb up the potential well to partially undo this mechanism of zeroing out to the neutron electric dipole moment. Okay, so just by taking the ratio of these two, you get the amplitude of the waves, which ends up being about 10 to the minus 19 radians. Okay, so this number explains why it's been so hard to detect QCD axion dark matter. When was the last time any of you have measured 10 to the minus 19 radians? Okay, so that's the particle physics part of the talk. One more thing. Since this is a CP violating angle, you can induce these rotations. There's this three-wave mixing interaction where the CP violating angle of, again, 10 to the minus 19 radians can induce through loop diagrams that suppress you by another 3 orders of magnitude. You can get a 10 to the minus 22 radian rotation between electric fields and magnetic fields. Okay, so the way that we typically search for this axion dark matter is we supply a huge magnetic field, because that's the largest energy density that we can possibly make, and look for electric field to emerge from it at a fractional level of 10 to the minus 22. Okay, so that's typically how these experiments work. And in the context of quantum computing, you have these dark matter waves coming in, and you have a high magnetic field in your experiment, and then you induce an oscillating electric field oscillating at the same frequency as this axion dark matter. And if your quantum RAM, some kind of microwave cavity, ends up being at the same frequency as these oscillating waves, then this magnetic field gets converted into oscillating electric field or single real photons inside this microwave cavity. Okay, so this, yes, please.
The next one, what is the content in the loop?
These are typically some kind of heavy quark, I think. These are typically some kind of heavy quark. Yeah, that's charged under this under this anomaly. Yeah.
Okay, so not necessarily beyond standard model quarks.
Yeah, that's right. There's this is a model dependent assumption that something that we know couples to the gluons still has to somehow couple to electromagnetism.
Okay.
Yeah. Okay, so this is how the ADMX experiment works. You have this microwave cavity. You have a huge magnetic field in it. The axion dark matter wave comes in. You can think of it, again, this three-wave mixing diagram. It scatters on the magnetic field to create single real photons occasionally inside this cavity. And if this cavity were the quantum RAM for your quantum computer, then again, the signal is that you started with zeros stored in your quantum memory, and suddenly you get ones, and then you can easily tell the difference between a 1 and a 0. Okay. There's two aspects of this that make the experiment kind of complicated. Okay, I guess I'll mention that you can write this all in the context of classical formula and Maxwell's equations. The dark matter ends up being a space-filling current that depends on the coupling constant, the amplitude of the wave, and the amount of magnetic field you're supplying as the second wave in the three-wave mixing. And the oscillations occur at a frequency equal to the mass of the dark matter. And you just plug this into Ampere's law, and then you get the power that you deposit is just a voltage times current, or force times velocity. So a couple of aspects of this is that the coupling is so weak. This is a very, very undercoupled signal because dark matter does not couple very strong to visible matter. That is good if you can make a resonant cavity where the size of the cavity is equal to the half wavelength. So as the dark matter wave comes in and pushes the electromagnetic field propagates across the cavity and comes back. And if this total travel distance is one wavelength, then it comes back just in time for the next crest of the dark matter wave to push it in phase. So it's just like if the dark matter is pushing a child on a swing, you want to push at exactly the right time to build up amplitude. So typically, to achieve this condition, we want the size of this cavity be equal to the Compton wavelength of the dark matter. Okay, and this will be problematic later. A second fact is that we have no idea what is the signal frequency. We don't know what the dark matter mass is. That's not something that the model predicts. The model only predicts a relationship between the dark matter mass and its phase transition scale. So what it means is that we have to do a radio scan over a very large frequency by tuning this quantum RAM, this microwave cavity, 10 to the 6 times per factor of 2 in mass, it turns out. Okay, so that means that it's not really a single experiment to discover the dark matter, but rather 10 to the 6 different experiments. You have to reconfigure the apparatus, integrate a little bit longer, reconfigure it again to search for a different mass. That's tuning the radio one step at a time and integrating at each tuning step. So it turns out we have to greatly increase the signal to noise ratio in these experiments in order to try to minimize the integration time at each step. Okay, the naive calculations using conventional technologies tell us that just a scan over a small region in frequency or mass space might take 10,000 years using conventional technologies, and that motivates why we need to move to quantum technologies. Okay, so here's a plot of photon rates, both signal and noise photon rates, as a function of photon frequencies. Where we're going from 100 megahertz to 10 gigahertz. So this is like 10 to the minus 6 electron volts to 10 to the minus 4 electron volts. Yes? Yeah.
The predicting the special extent, so to speak, of the dark matter wave, what would be special extension?
Oh.
What would be the flight time as well of the...
Okay, yes. Let's... Yeah, let's talk about that a little bit more. Okay, so the dark matter, we know that it's non-relativistic, because that's how, if it's relativistic, we call it radiation. If it's non-relativistic, we call it dark matter. We know that it's bound inside the galaxy by the gravitational well, and that's how the galaxy forms. So we know that its velocity has to be very slow, 10 to the minus 3 of the speed of light, because that's kind of the escape velocity from the galaxy. So any more energetic dark matter would just fly away and would not be bound. Okay, so if the velocity is 10 to the minus 3 of the speed of light, that tells us that the momentum gamma mv is 10 to the minus 3 of its rest mass of mc, and so that tells us that the correlation length, which is 1 over the momentum spread, is 1,000 times the Compton wavelength. Okay, so the velocity is 10 to the minus 3 of the speed of light, and the correlation length is 1,000 times the Compton wavelength.
So this would appear as a very short burst in your signal, for example, that with a periodicity which you don't know necessarily?
Well, I think one way you can think about it is it's very similar to a laboratory laser. So a laboratory laser might have a kilohertz line width corresponding to a millisecond coherence time. So if you shoot the laser at something, you get sine waves that are only coherent for a millisecond, and the next millisecond will be self-coherent, but these two segments of the continuous wave will not be coherent with each other. So the way you can think of the dark matter is exactly the same way. It's some waves that are in the background that are coherent for a certain amount of time. Of course, again, so the the escape velocity is 10 to the minus 3. This is the typo. So the kinetic energy spread of the dark matter is 1/2 mv squared, right, divided by the rest mass mc squared. So if v over c is 10 to the minus 3, v over c squared is 10 to the minus 6, then that tells you that the energy spread is 10 to the minus 6 to its rest mass. And so that also tells you that the wave coming in has 10 to the 6, 1 million coherent oscillations before it decoheres. Okay, so what you want to do is you want to make a cavity also that can be coherent for 1 million oscillations or 1 million round-trip traversals of this wave. And then that will match the line width of the cavity to the line width of the signal.
Are you sensitive to this coherent part of the wave, to the coherence of the wave?
Yeah,
we're detecting everything at the background as well.
We narrow band everything to 10 to the minus 6 line width, and that rejects all of the noise that's outside. So we have a frequency of let's say 10 gigahertz. We try to narrow band to 10 kilohertz. Did I get that right? Yeah, that's right. And that rejects the noise that's not coherent. Etienne, did you have a question?
On the same point, does that mean that you can expect an amplification, coherent resonance of the different waves by also typically a median of the dark matter wave signal? If I understand, you want a resonance inside your point.
Yes, yeah.
So if you say it can be coherent for 1 million time,
yeah,
you will have amplification by that amount.
Yeah, that's right. You know, just like if you're pushing your daughter on the swing, if you push 1 million times and then there's no losses, your daughter will go to very, very high amplitude. Yeah, until either you get bored and you start pushing at the wrong time and you decohere, or if the frictional forces on the swinging child create losses. Yeah. Okay. Okay. So all right. So the point here is that here I'm plotting the effective signal rates and background rates, so photon rates versus frequency of the experiment. So these are many, many different experiments operating at different frequencies. And so this is the predicted signal rate from a typical model of dark matter with order unity photon coupling for a cavity whose volume is a wavelength cubed, Compton wavelength cubed. And so again, you can see the problem as you go to higher and higher frequencies, the Compton wavelength becomes smaller. And so as the resonators, these quantum memories or microwave cavities become smaller and smaller, they intercept less and less of the dark matter that's coming in. Okay, so it's just geometrically, your signal rate ought to plummet, and it also falls for other reasons. But geometrically, as the detectors get smaller and smaller, you expect fewer and fewer photons per second. And the current experiments, for example, the Axion dark matter experiment, use quantum limited amplifiers to they look at the little sine waves that are built up in these microwave cavities, and they try to amplify them into big sine waves so that we can digitize and write down the data on a computer and take the Fourier transforms to measure the power spectra to see if there's excess power or not. Okay, so the problem with that technique is that we run into what's called the standard quantum limit, in that if you take a little sine wave and if you could noiselessly amplify it into a big sine wave, then If you could do this without noise, then in principle, you can measure both the amplitude and the phase of that little sine wave with infinite precision. But we know from quantum mechanics that we cannot get infinite precision on these measurements, that the quantum phase space is actually quantized in units of 1/2 h bar. Okay, so this amplification process must be susceptible to the 0-point noise of the original mode. And not only that, it's susceptible to the 0-point noise of the other modes that get mixed in with your original mode in the amplification process. And this is called the standard quantum limit. Okay, so it's limited by the 0-point fluctuations of the quantum vacuum. And effectively, the standard quantum limit, you can think of this as about 1 photon of variance in your signal per resolved mode. Okay, so you can think of that when you think about statistical mechanics, each degree of freedom has 1/2 kT of energy on average. And if you go to the quantum limit, each degree of freedom has 1/2 photon of noise on average. Okay, so 1/2 photon of noise, okay, you might think it's not that bad, but as you go to higher and higher signal frequencies, you're reading out your detector, you're resolving those modes faster and faster. And you're eating that 1 photon of noise faster and faster, and that's why this quantum noise increases with frequency. Okay, so the current experiments, ADMX operating at about 1 gigahertz, there's not so much difference between the background rate and the signal rate. So with this kind of difference, a couple of orders of magnitude, we can just make many, many measurements and average away the quantum noise. But if you go to higher and higher frequencies, this is too much of a difference between the noise level and signal level, and you cannot average this away without taking tens of thousands of years. Okay, so that's the issue. Okay, so the conventional techniques that we pioneered maybe 7 or 8 years ago were good for this regime, but not if we want to probe towards higher masses, higher frequencies. Okay, and that's kind of where the signals. So there's two things that we can do. We can either increase the signal by spending a lot more money on magnets. That's a very, very expensive way to do an experiment. But then we can use quantum techniques to reduce the noise. All right, so then just to kind of illustrate what we're talking about, this is a demo that I mocked up for my kids one morning, in which I have a Newton's cradle, so 2 pendula with the same pendulum length, so 2 oscillators that have the same frequency, and I coupled them with 2 refrigerator magnets. Okay, so there's some magnetic coupling between the 2 oscillators. I'm going to start this one swinging to model the dark matter, and this one is at rest initially. That models the photon state inside the cavity. And so this is pretty nice. Okay, so they have the same frequency. So every time this dark matter comes in, it comes in at exactly the right moment to deliver a coherent push to this receiving oscillator state, until eventually, if you had infinite coherence time, all of the energy in the dark matter oscillator would be absorbed by this cavity oscillator. Okay, so then that's what we call the first mixing maximum in things like neutrino mixing, where you suck all of the amplitude out of the original oscillator. So that would be great if we could do it, but it turns out, again, as I indicated in my answer to you, that there's a finite coherence time for the dark matter, because there's a finite energy spread. Higher energy dark matter just flies out of the galaxy. There's finite energy spread, so there's a finite coherence time. So you never reach the mixing maximum, and in fact, the best you can hope for is to transfer the occasional single quantum of energy. Okay. So to be a little bit pedagogical, this is how phasors, this is the phasor representation in kind of the XP phase space of an oscillator. So X is when the oscillator, the pendulum is at its maximum excursion and is being acted on by potential energy. And then P is the quadrature when it's swinging down and reaches its maximum momentum at the bottom of its swing before it goes back up to X. Okay, so this is kind of the classical representation of a phasor that you might learn in an undergraduate electrical engineering class. But in a physics class, we learned about Heisenberg's uncertainty principle, that you cannot localize the endpoint of this phasor infinitely well in XP phase space, because the quantum vacuum does not have any information on area scale smaller than this, 1/2 h bar. And so the endpoint of this phasor will actually look like a Gaussian blob with area 1/2 h bar. Okay, and then you can write this in polar coordinates to get the amplitude phase or the quantum number phase uncertainty relationship. And there's often a lot of debate about this, but I don't know why. It's just writing this equation in polar coordinates. Okay, so this tells us that we cannot know the amplitude of a wave and its instantaneous phase, just a sine wave. We cannot know those two quantities to infinite precision because nature does not have that information to offer us. Okay, so yes, yeah.
The experiment, the magnetic field is a static field.
In the experiments I was mentioning before, yes, this is just a static field. There's some people who do try to use a large RF field, but then there's other complications associated with those experiments because the static field can be very, very noise-free, whereas the RF field often has sidebands that would mimic your signal. Yeah. Okay, so again, this is kind of a diagram of XP phase space with this Gaussian blob. This is going to be the dark matter. It starts with a non-zero amplitude. And this is the receiving cavity state. It starts with a 0 amplitude. And let's see if I can get this going. Yeah. And so this is kind of the simulation of what's happening on. So one of these oscillators will spiral into 0 amplitude while this one spirals out to non-zero amplitude. Okay, so then looking from above, the way these experiments work is you prepare the vacuum state, again, in XP phase space, which is there's a blob, a Gaussian of area 1.5 h bar here, where the extent of this distribution in this quantum phase space represents the 0-point noise of the quantum vacuum. And then, so this is the initial state, and then there's some external force exerted on this initial state that displaces it to a distribution that has non-zero amplitude. Okay, you transferred some energy to this oscillator, so that now the phasor has non-zero amplitude. But now this is even an exaggerated diagram of how the new state has a very strong overlap with the original state. And so in order to detect that the centroid of the new Gaussian has been displaced, you have to average away this noise, the 0-point noise, over many, many measurements. In ADMX, we typically average over 1 million measurements to be able to resolve the displacements that we want to see. Okay, and again, this is all due to the Heisenberg uncertainty principle. And the way you can think about it is that the shape of these blobs indicates what's the resolution of the probe. Okay, so when you're trying to use a quantum limited amplifier to do the probe, you have very, very poor resolution for these displacements that are smaller than the 0-point noise of the quantum vacuum. Okay, so the idea we had when we engaged the quantum computing people was that they're used to making measurements like this all the time, and they're able to resolve differences between zeros and ones. And we want to do the same thing. We want to resolve the difference between 0 photon signal and 1 photon signal. So why do we have to do something like this? This seems like it's the worst possible way to try to measure the signal. So instead, we're going to do what they do, which is to change the states that we use to measure the signal. Instead of trying to measure sine waves in terms of sine waves with slightly larger amplitude, why not just use number eigenstates, the Fock states, the zeros and ones? Okay, so again, in this XP phase space, position momentum phase space, the Fock states can be represented in this cartoon as annuli, whose amplitude is equal to the square root of the photon number in that state. Okay, so amplitude squared is equal to the photon number. So you have the vacuum state again, which is this Gaussian centered at 0, and you have the n=1 Fock state, which is kind of an annulus centered at amplitude 1, and n=2 Fock state, which is an annulus centered at amplitude square root of 2, and so on. And so what we're looking for is the displacement of the original vacuum state, which is represented by this Gaussian blob, but the Gaussian blob has tails. Okay, so we know that the 0 state is orthogonal to the 1 state, but a shifted 0 state means that some of the tails of the Gaussian will leak into the 1 state. And so those two, the shifted 0 state is no longer orthogonal to the 1 state. And you can make the projection that's precisely the photon occupation number that's induced by that displacement. We're looking for the leakage of this displaced state into this n=1 state. And that's how we count photons. Okay. So secretly, that's also how we count photons in the classical detector. But this is the quantum mechanical description of it. And it'll prove useful later. So you're almost out of time. Yeah, that's fine. Okay, so the advantage of this is that there's no 0-point noise, okay, because we're measuring photon number. We're not trying to simultaneously measure two non-commuting observables like number and phase. We're just measuring number. And photon number also commutes with the Hamiltonian. So there's useful parts of that also later. So it means we're not fighting against quantum mechanics. So the final state basis already satisfies the Heisenberg uncertainty principle. So we don't actually lose anything by projecting into this final state basis. There's no 0-point noise that's going to kill us. And so it's in photon counting detectors, the measurement noise, so the Poisson noise from dark counts can be made arbitrarily low. There's no quantum limit on it. And so there's many different examples of how we can do this. One is just, here's a microwave cavity that has big holes in the side for some technical reasons, but the holes are smaller than the wavelength of the light. So the wavelength actually stretches across this entire region. It's about wavelength of a few centimeters. And so what we've done is we put a superconducting qubit, one of those Josephson junction devices I told you about, right in the middle of this cavity. And as in the qubit, you can't see it. This is kind of like millimeter scale antennas. We put millimeter scale antennas on the qubit. So as the electric field of the photon oscillates up and down, it's picked up by the antennas. And then the response is it drives a current through that Josephson junction. And I told you the Josephson junction has an inductance, which is nonlinear in the current. So if there's a really tiny current sloshing through that junction, it changes its inductance and it changes its LC oscillator frequency. Okay, so that's how you detect the photons. So if you take the spectrum of this device as you drive the device with a sine wave, you get the Poisson spectrum. So in this case, we're exciting it with typically about 1 photon occupation number. So sometimes you'll measure 0 photons within the lifetime of the cavity. You measure 0 photons, and so this will be the frequency of this qubit that you measure by probing it, by bouncing other waves off of it to see what its resonant frequency is. Occasionally, you'll get 1 photon in the cavity from the drive, and that 1 photon, again, induces the nonlinearity in this qubit and shifts its LC frequency. Okay, so you see a peak in the response corresponding to n equals 1 photons. And then again, with the Poisson distribution of photons in here, sometimes you get 2 photons. So the electric field that's driving the current is actually quantized in units of the number of photons that are in there. So you might get 2 of these shifts, and you see another peak in the response corresponding to 2 photons in the cavity. Okay, so this is a very interesting way of measuring photons, because these measurements do not touch that original photon that is stretching out across the length of this device. It's all we're doing is measuring the frequency of the qubit that's being driven by that 1 photon. But the important point is it's being driven at a subquantum level, so it never absorbs that single photon. You can make this measurement over and over again. All you're doing is measuring the frequency of this LC oscillator and inferring the existence of an oscillating electric field in the background. Okay, another way you can think about it is for n equals 0, you still have vacuum fluctuations that are driving vacuum fluctuations in the current, and that gives you the n equals 0 frequency. So that's a Lamb shift on the qubit. If you think about it as an artificial atom, it's the radiation pressure from the 0-point photons. And then if you have 1 photon, that exerts additional radiation pressure on this atom, on this artificial atom. And you have 2 photons, that exerts even more radiation pressure. And so what you're doing is you're trying to measure the existence, the presence of these additional photons by the radiation pressure that they are exerting on this artificial atom. Everybody happy with that? Since I don't have much time, I'm going to skip ahead. Since then, there's been other experiments that detect the single microwave photons in the axion dark matter experiment concept. So here's an example from my colleague Patrice Berthet and his colleague Emmanuel, I forget his last name now, but both at Saclay, in which they again have the microwave cavity inside a magnetic field. The single photon builds up inside the cavity. Eventually, it leaks out and goes into this chip superconducting qubit chip that's safely outside of the magnetic field. Okay, qubits don't like to live inside magnetic fields. And on this chip, they catch that photon, and then they execute a four-wave mixing process, a photon-photon scattering process, where they have the qubit as a nonlinear element. They pump on the qubit, and they take in a signal photon. And if the pump and the signal photon energies sum up to be equal to the energy to excite this qubit and the energy to send another photon into this separate cavity, this is called a waste cavity, to make the process non-reversible. If you have this energy non-conservation condition satisfied, then the qubit gets excited if and only if there's a signal photon present. Okay, so it takes the single quantum of information that's present in the single photon coming in and stores it as an excited state of the qubit. Okay, so this is an example of quantum information processing, taking information from your experiment and storing it in your quantum computer. Okay. So the next step is to make a quantum processing pipeline. Okay, so again, you have single photon signals possibly coming in through into your memory buffer, and you execute the four-wave mixing process. So if this photon is present, this photon combined with the pump photon that you send in has enough energy, exactly enough energy to excite this qubit from the ground to the excited state and produce a second photon that continues on down the pipeline. And so this detector executes a click. It thinks it's seen a photon. Okay, but the information has not been destroyed in this process. It's still here. The single quantum of information still propagates down this pipeline, and the same process happens again when it encounters the second qubit. So you pump on the second qubit, and you take in the energy from the single quantum of information here. And if the energies are exactly right, you excite the second qubit and send the information again as a single quantum down the pipeline. And you can do this many, many times until you have many, many qubits that all say, yes, yes, we think we have detected a single quantum of information. We think that we have detected your dark matter. Okay, so this is an example of using a rudimentary quantum computer as a data processing pipeline, processing the information at a single quantum level prior to amplification. And perhaps this will find use in a variety of different experimental contexts. Okay, so just to give you an idea of where we are, again, this is the photon rate, the prediction for the signal level, which again shrinks, falls rapidly as you go to higher and higher frequencies. Originally, we had the standard quantum limit background from the 0-point noise. Now, we've already reduced this background rate by 4 orders of magnitude with our current devices, maybe even 5 orders of magnitude. So we're very, very close now to being able to do these kinds of experiments, because now there's a much smaller gap between the background rates and the predicted signal rates. And we're very close to the regime of having experiments that are completely background free and dominated only by signal statistics. Okay, so I think I'm completely out of time. Perhaps this is a good time to stop, you think? Yeah. Okay, so I did have a couple of other topics I'm happy to talk about later. I'm glad we had a bunch of questions though, but so one other topic was, so we're kind of stuck here. If we're completely background free, the only way that we can make our experiments work is if we increase the signal rate, and we're kind of limited by the signal photons that we can capture in a reasonable time scale. So one idea is to use stimulated emission, which is to use this formula of force times velocity. So you can start your receiving oscillator at a non-zero velocity, then for the same force that's applied for the dark matter, you can transfer more power. Okay, so there's quantum tricks to start this cavity oscillator with a non-zero velocity, so to make this possible. And I'm very sorry that I didn't have time to get to some of these interesting topics. This is the actual demonstration of, as a function of injected signal, how much signal output we get from the stimulated emission processes that I'm talking about. And so as we increase the initial velocity, the initial occupation number of the cavity, we can greatly increase the signal rates. Okay, so in effect, stimulating the emission of signal photons from the dark matter. maybe I'll just finish on this slide. This is kind of the vision for the future, to use quantum computers like this as the front-end electronics for high-energy physics experiments. And I already mentioned a number of things. We can use quantum networking technology to do single photon frequency transduction. So we can use fixed frequency quantum computers to read out signals at various different frequencies from your detectors. I already talked about the signal processing pipeline. I didn't talk about analog signal integration, but in principle, there's no reason to integrate the signal in your big, unwieldy, high-energy physics device. You can integrate the signals in the qubits in the quantum computer. I've already talked about the noiseless readout, and so we're already a factor of 100 times below the 0-point noise with the qubit technologies. And then I didn't have time to talk about the deployment of these non-Gaussian resources to speed up time, but we have demonstrated that that's possible. I think I should conclude there. Yeah, thank you.
Thank you.